Okay, this is my practice talk for when I'm talking in Portugal. I think the best way to see how close you are to being ready for a talk is to just try and give it and see what happens. So that's the plan. Okay, and I should time myself to some extent because the talk's supposed to be 25 minutes, and I'm suspecting it's going to be too long, to be honest. Can I see the time when I have this open? I can see the time when I have this open, and does this thing record the thing? It does. Okay. Uh, the first thing I'm noticing is the first slide has the text too high. There's probably a lot of things like that throughout, which I'll fix afterwards. Okay. I'll start when the thing in the corner changes so I can accurately record the time. Okay, so the talk is about Thompson partition monoids. So in Portugal, you will have just heard some talks about Thompson groups, so you're probably familiar with Thompson groups, and I do not know how familiar my audience will be with partition monoids, but I will explain uh, both background on Thompson groups and background in partition monoids in some level of detail, and I'll explain how essentially the focus of the talk is a new monoid, which I call the Thompson partition monoid, which combines the ideas of the partition monoid and the Thompson groups. And it also gives you sort of an interesting framework for building new monoids, which correspond to sort of partition monoids, but for specific classes of algebras, which people might care about, given that universal algebra is a big thing. It sort of there seems to be a decent overlap between people who like universal algebra and people who like the partition monoids. Okay. Also, I mean, yeah, I'm a big Thompson Group fan, and clearly the audience will be as well. So I should say that this is joint work with my friend and colleague Naftali Kolodny, who is in the US right now. He works at Binghamton. He's currently a PhD student. Um, and yeah, the Thompson is Richard Thompson of the Thompson groups. Okay, so outline of the talk. So I'm going to explain the Thompson groups. I'm going to explain the partition monoids. I'm going to explain how the partition Thompson monoid works. It combines these two ideas. PV is the name of the Thompson partition monoid, where V is the Thompson group, and P is the sort of saying what you mean the partition monoid. And then we need to talk about Janssen-Tarski algebras. There's lots of different equivalent ways of defining PV, and the same way there's lots of different equivalent ways of defining the Thompson groups. And I think the sort of most beautiful idea in this case is using the Janssen-Tarski perspective. So I want to explain that a bit. But before that, I want to make sure you just know how to write down elements and multiply them and stuff. And then there'll be time for people to ask me questions. I have a lot of questions that I want other people to solve. I mean, I'm happy to solve them myself, of course, but I want to sort of leave them as open questions for people to think about. Okay, so what's V? So the first thing you need to know to understand V is binary trees. So an element of V in the end is going to be a pair of binary trees with a bijection between the leaves. At least that's the viewpoint I want to start with. So a binary tree, you have a root, it's this thing at the top. I assume you can see the mouse in the thing. Indeed you can. Okay. So this binary tree has 3 leaves. The leaves are the nodes at the bottom of the tree, which don't have any children and have nothing coming out of them. So this is a 3-leaf binary tree. This one has 4 leaves here. This one has 4 leaves here. This one has 6 leaves. 1, 2, 3, 4, 5, 6. And this one has 3 leaves. So basically, you just have a root at the top, and each node is either a leaf or it has 2 children, which are sort of ordered the left child and the right child. The left child is labeled by a 0, saying I'm reading a 0 to go to the left child, and the 1 is going to the right child. So I think of this leaf as the address 0, 1, because to get there from the root, I have to read a 0 and then a 1. So this is binary trees. And then, crucially, you can make binary trees with any number of leaves you want. Just any finite number of leaves you want. Any finite non-zero number of leaves you want. Okay, so what's V? V, an element of V, at least in this perspective, is a pair of trees with a bijection between the leaves, and we also care about them up to this a certain notion of equivalence, which I'll talk about in a second. So the way this is typically denoted is you write down the two binary trees like this in a pair, and you write letters below the leaves to indicate the bijection. So here I have I'm mapping this leaf to this leaf, for example. Okay, and here is another example. You might ask, why did I use these letters? So first, the letters I choose don't matter. They're just describing the bijection. But this tuple here, this pair of binary trees, is equivalent to this pair of binary trees because I only care about the tree pairs up to these notions of expansions. So if you look at the top tree here, you can obtain this tree from this tree by taking this leaf E and splitting it into two leaves B and C. And if you see the same address on this tree, I've also split this into two leaves, B and C. So if I can go from one tree pair to another one by taking leaves and splitting them into pairs of leaves and extending the bijection accordingly, so this E to E became BC to BC, then these things are called equivalent, and we think of these as sort of the same element. And you can go back, of course, because like equivalence relations are symmetric and transitive and stuff. Okay, so we care about trees up to this extension thing. A tree pair is up to this expansion relation. So that's V. And how do you compose them? Well, I've got these two elements, these two example elements. I believe this is the element X naught. It's an important element of V. So here, I sort of want the middle trees to line up, and then I can just sort of delete them. So I expand both trees to make the middle ones line up. So here I expand this tree at A so that I get this tree, and that also forces me to put an extra thing here. I also expand this one at C so that I get this tree, like the same tree in the middle, and I also have to expand this one at C here. And now that the middle things match up, I can just sort of delete them, and I get a new tree pair at the end. This is X naught squared. That's how composition works, and you can show this as associative. You can the other ways of looking at V make it more obvious this is associative, but this is the perspective which is going to be useful for partition monoids. And a particular thing I want you to keep in mind is that an element of V is two things and a relationship between those two things, which is also going to be true of partition monoids. So what are the partition monoids? So unlike V, the partition monoids, at least the standard ones, sort of the classical ones, are finite, and there's one for each number. So you can think of them as like the transformation monoids, or the symmetric groups if you like group theory. So Pn, n is a natural number, and for each n I have a partition monoid. So this is an element of P, so this is two elements of P5. Each of these is a partition. So 5 comes from the number of nodes in each row, the way I've written it. So here I've got 1, 2, 3, 4, 5. So an element gives me two columns of size 5 in this case. And I view an element as a partition of these two columns of 5 things. So this partition is the one which identifies these 3 nodes and these 4 nodes. And it's like totally arbitrary how I've drawn these edges. I want the edges to be enough edges that I've explained what the equivalence class is. The exact choice of edges I chose is not important. So if I had an extra edge here, for example, it would be the same element. And here's another element of the partition on 5 things. Okay, and this is sort of extends the some of the standard monoids in semigroup theory. So in group theory, the home for all your groups is the symmetric group, and these elements of the symmetric group are permutations. So S5 consists of permutations of 5 points, and in semigroup there's lots of analogs of this. So the sort of standard analog of Cayley's theorem in semigroup theory is that every monoid with n elements embeds into Tn, the transformation monoid. So this is just functions from a set to itself, and there are various other expansions of this. There are alternatives to this. There's the symmetric inverse monoid, which is the partial bijections from a set to itself, and there's the partial transformation monoid, the partial transformations, and the partition monoid is bigger than all of these in a way which I'll explain in a minute. So this is sort of it's continuing the theme of having a home for all semigroups, but we're being sort of more general as we go up. So in particular, it contains the symmetric group. And so here are 6 elements of P3, And if you're familiar with the finite symmetric groups, you might notice that these are the elements of S3. So this is the identity permutation. This is the swap the top two things permutation. This is the swap two bottom things. This is the swap top and bottom. And this is one of the 3 cycles, and this is the other 3 cycle. And here are some elements of the partition monoid on 2 points. In particular, there's a decent number of them, unlike the symmetric group. The symmetric group only has 2 permutations on 2 points. This one has many. I don't know how many. It's like the number of partitions of 4 points. So here's some of them. Only this one is in the symmetric group. This one's in the symmetric inverse monoid, and this one's just in none of the other things I've described. So this is just saying everything's the same. Okay. So how do I multiply these things? I'm claiming this is a monoid, so I have to tell you how to multiply them. So I've labeled the nodes using numbers here, because I want to talk about the various ways of thinking about this in a second. But the numbers here are just similar to the letters in V. The numbers are not important. They're just sort of labeling the nodes so I can talk about them more clearly. So here's 2 elements of the partition monoid. So this one connects this to this, connects this to this. This is a block, and these are like singleton blocks. Similarly, this is a block of size 4, and this is a block of size 3. I probably want to make these pictures a bit more tidy when I do the actual talk, and I think this is sort of inconsistent with this, but okay. But yeah, the edges don't matter, so this is all technically correct. So what do? Well, similar to V, I want to sort of make things match in the middle. So I stick the pictures together, and then I just sort of make all consequences of what I've got. So if I stick these 2 pictures together, I get this. I've just identified this column with this column, and I got this picture. And now I have a partition of 3 lots of 5 things. So I just have 3 lots of 5 things and some edges between them, and I think of the edges as saying these things are equivalent. So now there's a path from this 4 to this 4 now, which goes via all of these things. So in this sort of partition of 3 sets of 5 things, this 4 is equivalent to this 4, and like this 1 is equivalent to this 2, and so on. So we sort of look at this as a partition of these 3 sets of 5 things, and then we ignore the middle set, which doesn't matter anymore, but we remember now that this 4 is now connected to this 4, for example. So we get this, and like this 1 goes to this 2 via this, and this 2 goes to this 2 via this. And that's how the composition works. And you can check this as associative. It's kind of tedious, but it works as you'd hope it works. Okay, so another way of thinking about this, which I think I find very useful and will be sort of more related to the Jonsson-Tarski stuff later on, is equivalently, this partition can be thought of as a bijection between 2 quotients of the set of 5 things. So this, for example, this way of viewing 5 things, I have an equivalence relation on this which sticks 3 to 4 in the picture, and it doesn't stick 1 to anything else, and it doesn't stick 5 to anything else. So I get this partition of 5 things. So now I'm only looking at partitions of one side at once right now. This one has the trivial partition, or I guess it's the equality partition, is the one which only has blocks of size 1. And then the edges between the 2 small partitions give me a partial bijection between the 2 sets. And this is true of all partitions. It's not too hard to check. So every partition corresponds to a partial bijection between 2 quotients of a set of 5 things. Like 5 is not special, it's just an example number, but yeah. And similarly, this one corresponds to this partial bijection. Here I've stuck 3, 4, and 5 together, and I'm just mapping that to 4. And you can compose them in a nice way. So you sort of take the least, or the coarsest partition, which refines both of these 2 partitions. Or is it coarsest or finest? Finest is a small pieces. Coarsest is you've got bigger blocks. Yeah, so it's the coarsest partition which refines both of these 2 partitions, and then you have. Now you're just composing partial bijections and you get this. And you'll see, and if you sort of unpack it, this is the same answer as this. So you can alternatively think of this as these partial bijections between quotients. Okay, so here's just sort of the structure of the submonoids. So this is the partition monoid at the top. Here's an example element of the partition monoid on 3 things. This is the partial transformation monoid on n things, or in this case 3 things. and this is an element of this. So you can, this is sort of giving you how you embed the partial transformations into the partition monoid. So this is our partition. You can think of it as the transformation which maps 1 and 2 to 1, and then it's just undefined on this. And in particular, the way that we're embedding it, we have this trivial partition on the right all the time, at least for this one. And this is assuming you want to compose functions from left to right. If you want to compose them from right to left, you could have the trivial partition on the left, and then it would be sort of equivalent. Okay, and then the transformation monoid is the same thing, except now everything on the left has to go to something. The symmetric inverse monoid, so this is partial bijections from a set to itself. So this is the same thing from before. We had partial bijections between quotient sets, and now we just don't quotient the sets, and we still have partial bijections, and that's fine. This is the dual symmetric inverse monoid. This is full bijections between quotient sets. It's an important inverse monoid. Here's an example. So I've stuck these two things together on both sides, and I have the identity of partial bijection on the quotient there. And then the symmetric group I mentioned before. This is an element of S3. This is a 3 cycle. Okay, but this is sort of the structure of what's going on. You have the symmetric group and various ways of generalizing the symmetric group. And this is going to sort of be analogous to what happens in VLAN. Maybe I'm talking too fast. I don't know. Okay, so tree pair partitions. So this is sort of combining the two ideas from before. So partitions, I had two partitions of a set. So I have a partition of two copies of a set, or equivalently partial bijection between two quotients of a set. And in tree pairs, I had two trees. I had a pair of trees, and I had a bijection between the leaves. So the tree pair partition is sort of the combining these ideas. I have two binary trees, and in this case I actually care about all the nodes, not just the leaves. And I have a partition of the nodes. So here is a pair of binary trees, and similar to the Thompson notation before, I take this is like in the same block as this, and so on. And here's another element. So you can just take you take any two binary trees and you have a partition of the nodes. But unlike the partition monoid, you have to be a little bit careful. So you have to satisfy a certain condition. So the binary trees have this sort of structure where each sort of parent has two children, and you want this structure to be respected by the partition in some sense. So in particular, this kind of thing isn't allowed. I'm not allowed to have two parts of my partition. They can be like the same tree or different trees. But if I have a tree pair partition, and I have two nodes labeled A, which are both parent nodes, then their children need to have the same labels. So this is sort of a structure preserving thing which needs to be there. And sort of dually, I can't have two parent nodes with the same children, like the same block partition, with children in the same blocks, but which are not in the same block. So like two parent nodes have the same label if and only if both their children have the same label. We need this condition. But other than that, you can have any partition of any two binary trees. And like with V, we only care about these things up to a certain equivalence relation. But it's quite nice. Okay, so how do expansions work? So with V, you could take any leaf, and you can look at this maps by the bijection to a leaf on the other tree, and you can expand at that leaf, and that gives you an equivalent thing. So here's some examples of equivalence things. Here's a tree pair partition. You can check it satisfies the conditions if you want. In fact, maybe it would have been helpful if I'd gone through that here. So here's like an example. You look at B. Let's find two parent nodes. Do I not have any parent nodes? Maybe this was a bad example because there's nothing with two parent nodes. All right, well, like there's no two parent nodes anywhere in this tree which have the same label, so this can't break. And I don't believe there's any two nodes with the same child nodes anywhere, so this can't break it either. But like, for example, if this was an A, then that would not be okay because the left child of A is supposed to be B and the right child of A is supposed to be A. So this is not allowed to be an A, for example. Okay, so in this case, I have this and I can expand it in some sense. So here, this way, I've expanded it at this thing. And unlike in V, you don't have to expand on both sides at the same time. You can be a bit more loosey-goosey. Yeah, and this is sort of going to generalize V, so you might say, doesn't that mean you could be loosey-goosey in V? And that's kind of true, but in practice you usually don't want to be as loosey-goosey as this, but it will sort of be necessary in the partition monoid case. Okay, so I've added 2 children to B, but you'll notice I've called them B and C. So I haven't just sort of added 2 things and considered them to be new things. I've added 2 things and considered them to be the same as old things. And why did I do that? I did that because I want this condition to still be true. So you sort of make the new things as distinct as possible while respecting this condition. So in this case, B has been given 2 children, but I already know in this partition that if I have a B, its left child is supposed to be called B, and its right child is supposed to be called C. So when I gave this B 2 children, I had to respect that, and I gave the left child the label B and the right child the label C. So down here, I could have expanded C for no reason, and I give this 2 children, but now C doesn't appear as a parent anywhere in either of these 2 tree pairs. So the 2 children of C now have new labels, which I called E and F. So these are all the same tree pair partition up to the notion of equivalence of the Thompson partition monoid. So these are all the same element of the Thompson partition monoid. Okay, so how do I compose them? Well, it's sort of similar to both V and the partition monoid. I want to make the things in the middle look the same, like by making as few changes as possible, and then I just sort of see the consequences of that, and then I delete the thing in the middle. Okay, so these 2 are different, and the middle trees are different, so I want to expand the left one to have the same shape here as this has here. So I expand this B, I give it 2 children, and as explained before, when I do this, I have to give this the label B and this one the label C, because this B already has a left child called B and a right child called C. So I do that, and I get this, and then I identify these 2 trees, so D is forced to be the same as E, A is forced to be the same as F, and this is what's going on here. B is forced to be the same as F, and C is forced to be the same as F. So lots of things are F now. And then I see what happens. So there are some consequences of this. If so D equals E, if A equals F and F equals B, then A equals B. And there's a bunch of consequences of this which make lots of things the same. And then if you relabel according to these, first G is equal to A, so these G's became A, and then I just delete this middle tree and I get this thing. And like basically everything has become A now except this node at the top. So now I have a much more coarse partition, and generally the partitions get coarser as you multiply more things, similar to in the partition monoid. Okay. And also this monoid contains the partition monoid in a fairly natural way. You can take like a sort of the freest binary tree of a given size. So if I have a binary tree with like n nodes and I just don't stick any of the parent nodes together, then this gives me like a copy of the partition monoid on n point. Okay. Yes, so actually there's an issue with this, which I've swept under the rug. So I said it's just really nice that you can sort of expand things anywhere you want, but you have to be a little bit careful with this, because if you don't expand things enough, sometimes you get the wrong answer. So in this case, this is the correct answer. I checked it, but it's theoretically possible that you make some expansions, and this is unlike the partition monoid or V. If you make some expansions in the middle, you might still get the wrong answer because you didn't expand enough. Sometimes you need to make sort of more expansions and then you get a different answer. But once you've made enough expansions, making more expansions will always still give you the correct answer. So you have to either do this and be careful you made enough expansions, or there's another way of doing this, which is equivalent, and I want to talk about that now. And the equivalent way, you have to be much less careful about how much expanding you do. In fact, there's no expansions to do at all. But I want to talk about this perspective first because it's where I think it's most clear how this comes from both V and the partition monoid in this perspective. Okay, so with machines. So a tree pair partition corresponds to a machine. So, or like an equivalence class of tree pair partitions. So in particular, before I had an equivalence class of tree pair partitions, and I want to be careful about how much they were expanded. But now I can just take one of those classes and turn it into a machine, and I just get one machine, and I can use the check if things are the same element. I'm just checking if the machine is the same, and the machine's also sort of better for multiplying things. So in some ways, this representation is sort of better. Okay, but the machines have to be trimmed, deterministic, transition collapsed FSA with 2 start states. So the 2 start states sort of come from these 2 root nodes. And what are the nodes of the tree? Well, so what are the states of the machine? Well, they're just sort of the equivalence classes of this relation. So the first one would have one node for A, one state for A, one state for B, one state for C, one state for D, and so on. And then what are these other words? So finite state automaton is just like a machine. You've got some nodes and some states and some errors between them. And transition collapse is a technical condition. It sort of corresponds to this thing. So basically it says if I have two states with the same transitions and all the transitions are defined, then those states were the same. And that's it's saying this condition is true, basically. But like most machines have this condition. So you shouldn't be too scared of this condition. And it's like very easy to check if a machine doesn't have this condition. You can do it certainly in quadratic time, probably even linear. I haven't really thought it through, but it's easy. Okay. Deterministic just says like it's the second one of these things. This is sort of a standard automata word. You can't have, I guess this one's deterministic. You can't have, sorry, this one is transition collapse. This one's deterministic. You can't have a state which can read the same letter to go to two different places, which is what would be happening here. Here, A would read a 0 to go to B and to D, which is not all that. Okay, and trimmed just says get rid of sort of messy stuff which doesn't do anything. So in this case, this state C here wasn't really giving you any information. Like there's sort of an expansion going on at B. I mean, this B gives you information, but here we're just saying when you read a 1 from B, you go to some new thing. So it's sort of which is sort of like what you would guess. So like you do sort of the freest possible thing by default. And we sort of trim off this information. And the reason we do this is because it makes the machine smaller and because it means you have sort of unique representatives. Okay, so here's an example machine. I just took a random thing which has got two start states and I'm imposing all these conditions. So I determinize it. So you notice in this case, this node became the same as this node when I go over here, and that's because R can't have two ones coming out of it. In this case, I collapsed some stuff. So I think this state became the same as this state because when it reads a 1, it goes here, and when it reads a 0, it goes here, which is the same as this. So these have the same transitions, so I collapsed them, and then I trimmed, because this, you never get to this state from any of the start states, it doesn't matter. This is sort of free information, it doesn't do anything. And this is also sort of free information, it doesn't do anything. So this is sort of the natural way of viewing this machine in my framework. So if you want to have an example of an element of PV in this framework, you can just make some random two start state FSA, and then you perform this process and you get this sort of simplified thing. And these simplified things are the elements of PV. Or at least they're equivalent to the elements of PV. Okay, so here's an example conversion. So here's a binary tree. Here are my two binary trees from before. I take A became L, D becomes R, and then B became this state, and C's gone away because it was sort of free and not needed. And here E's become L, H has become R, and then F is this state, G is this state, and I think that's all of the letters. And you'll notice here the R, when it reads either letter, it goes to this state, because that state to G. So this is sort of corresponding to this. And then how do I compose the machines? I can compose machines either by composing the trees and then converting back, or more elegantly, I can just sort of stick the right start state of the first machine to the left start state of the second machine. Then I get this messy thing. And then I just perform the process I described before. I determinize, I collapse states, and then I trim in that order. And if I do that, so this is the thing I get from sticking these two things together. If I do all these things, I get this, which is the same answer as before. So how did I get to this? Well, let's see. So M reads 1 to get here and 1 to get here. So this state got stuck to this state. Similarly, this state got stuck to this state. And then M got deleted because you can't reach it from L or R. And this state seems to have gotten stuck to, one of them got stuck to L at some point. Because L reads 0 to get to here. This gets stuck to this one. This gets stuck to this one. And then I read 0, 1. I should study these more before I give the actual talk. That's good to know. Okay, but if you go through the process, you'll see that this collapses to this. Okay, So how long was that? That's like 28 minutes. So I'm already going too slow, or at least I'm saying too much. Okay. So Janssen-Tarski stuff. So what's a Janssen-Tarski algebra? The Janssen-Tarski algebras are a variety of algebras. You have a binary operation symbol and two unary operation symbols. And they essentially say we have a bijection from the set to itself. So J is the underlying set. Alpha is a bijection from J to J squared. So alpha naught and alpha 1 give you the components of this map. And I'm saying it's a map and the laws of the variety say that this map is the inverse of lambda. It's the two-sided inverse. And this is a variety because it's defined by some laws. And this is sort of it was introduced by Janssen-Tarski as a variety which has the property that the free objects of non-zero finite rank are all isomorphic. And the bijection from the set to its square sort of allows you to force a single free generator to be equivalent to two free generators, and that's vaguely how it works. This is an important variety of algebras, and it's famously, if you look at the free Janssen-Tarski algebra, so the unique Janssen-Tarski algebra of finite non-zero rank, did I say free there? The unique free Janssen-Tarski algebra of finite non-zero rank, its automorphism group is Thompson's group V, and this is one of the important ways of defining V, and I think it's one of the coolest ways personally. Okay, so what's a Janssen-Tarski unary algebra? Well, this is a term which I made up, which basically just says you've got the same conditions except you don't have lambda anymore. And this is no longer a variety, it's what's called a quasi-variety. I want alpha to be injective, which is the best you can sort of do without the lambda. And this is not like a law. I'm not saying that this expression is equal to this expression. I'm saying that if this expression is equal to this expression, so if the pair of outputs of alpha is equal to the pair of outputs of alphas of a different thing, then the original things were the same. This is an implication of equalities. And this is like you get what's it called a quasi-identity, which defines a quasi-variety. And quasi-varieties have a lot of the properties of variety, so this is going to be good. So like, why did I define this? Well, I did this because unary algebras are really nice to work with compared to general algebras. Like, you can just like take unions of stuff and it all works nicely, and free products are nice, and free unary algebras are very straightforward. So this is sort of easier to work with, and it turns out that the quasi-variety of Janssen-Tarski unary algebras is almost exactly the same. Like, it sort of carries almost all the data of the variety of Janssen-Tarski algebras. So you sort of work in this framework a lot. And it also relates back to the pictures from before. Okay, so as I was saying before, a finitely presented Janssen-Tarski algebra. I'm going to talk about presentations because presentations correspond to quotients of free objects. And before, when I was doing partition monoids, I was taking quotients of my finite sets. And now I'm going to try and take quotients of an algebra instead of a finite set, and that's going to be the relation. So my finite presented Janssen-Tarski algebra is basically the same thing, and I'm hand waving now. If you do the theory, you'll see it's basically the same thing as a finitely presented Janssen-Tarski unary algebra, and that's the same thing, basically, as a binary tree partition. So a Janssen-Tarski unary algebra, I have a finite number of generators, and I've got two unary relations, like I've got a left and a right. So I have like two children for each element, and this sort of goes on down the tree, as it were. So this has a very strong relation to binary tree partitions, and the two conditions on the binary tree partitions I imposed are exactly saying that the sort of quasi-laws of the Janssen-Tarski unary algebras hold. And these are the same thing as I explained before to these nice automata. So I want to think about finitely presented Janssen-Tarski algebras as basically the same thing as these automata, and that's going to be the way of viewing it. So the automata will correspond to my nice algebras, and these sort of links between these two automata give me elements of the partition monoid, the Thompson partition monoid. Okay, so V, as I said before, is the automorphism group of the free Janssen-Tarski algebra. That's equivalent to the tree pair bijection thing I said before. Pn is the monoid of bijections between subsets of quotients of 1 through n. And so if I combine these in this framework, the PV is the monoid of isomorphisms between finitely generated subalgebras of finitely presented Janssen-Tarski algebras. So we have a monoid which describes all like partial isomorphisms between all finitely presented things in this variety. And it's like really sort of tidy, and it's like you can solve the word problem. I just gave you some machines for solving it before. So this one monoid describes basically everything you want to know about this variety, assuming you're focused on finitely presented stuff. So it's a very cool monoid in my opinion, and it generalizes the V in the partition monoid. Yeah. Okay. So this is the sort of the partition Thompson monoid analog of the thing from before. It's been 33 minutes now, so I've kind of cut down quite a lot of this. So PV is the big thing. It corresponds to the partition monoid. There's also other versions of V, which have been studied by Berger and the like. So this is, I think Berger called this monoid INV 2.1. This is the partial transformation version of V. There's a transformation version of V. There's a symmetric inverse monoid version of V, and there's a dual symmetric inverse. There's a dual symmetric inverse monoid version of V, and then there's V, of course. V corresponds to the symmetric group. Okay, and this one I think is pretty cool. It hasn't, I think, so PV and IV star are both new. The other ones have been looked at before. In IV star, it consists of the isomorphisms between finitely presented Johnson-Tarski algebras. So in particular, it contains the automorphism group of every finitely presented Johnson-Tarski algebra, and those appear as the group H classes of this inverse monoid, which I think makes it a very interesting monoid to study. Okay, so here's some theorems. That was just lots of background. So the paper with Naftali, we proved that PV is finitely generated. We prove it's not congruence-free, which is interesting because V is famously a finitely presented infinite simple group, and simple means congruence-free in group theory land. TV, IV, and PTV are all known to be congruence-free, so this sort of breaks the pattern. We have proper quotients now. So the first thing you do when you've got a new semigroup is you look at the Green's relations. So the R relation, L, D, and J relations work very similarly to the way they work in the partition monoid. So R says you have the same Johnson-Tarski algebra on the left, and particularly this is a sort of motivation for why this was a good way of studying these monoids, because if we just use sort of the nice automaton descriptions, R, L, D, and J are just much messier to describe, but now it sort of works more nicely and more similarly to the partition monoid case. So R says that they have the same domain Johnson-Tarski algebra, and the finitely generated subalgebra that your partial isomorphism is coming from is the same, like equal. L is the same but backwards. D says that your partial isomorphism between quotients are going between isomorphic things. So you're just looking at the partial isomorphism. Now you actually don't care about the quotient. You just care about the isomorphism type of this particular sub-algebra of the quotient. And as is sort of common with J and D, J sort of corresponds to bi-embeddability kind of things. So J says that the same algebras from D, instead of being isomorphic, they embed in quotients of each other, which in the finite case is the same as being isomorphic. But in the infinite case is not the same. And we also prove that you can decide all of these things. So in doing so, we decide lots of things about how Johnson-Tarski algebras work, which is independently interesting in my opinion. So there's more theorems. The finitely presented Johnson-Tarski algebras are coherent, which means that every finitely generated subalgebra is finitely presented. We can solve the word problem, we can solve the subalgebra membership problem, and we can solve the isomorphism problem. So we can solve basically everything you want to know about finitely presented Johnson-Tarski algebras, and this allows you to solve these Green's relation problems. Okay, so things that I want to know. Is PV finitely presented? Because the other Thompson monoids all were, so V is. TV was proved to be finitely presented in a paper with me and Bill, and in a paper that I think Alex just talked about 30 minutes ago, if we're in Portugal right now. It's known that we proved that IV and TPV are finitely presented as well. So this is sort of the next step. And the question about, we already know it's finitely generated. We proved that in the Naftali paper that I'm giving the slides on now. So the next question is IV star finitely generated? So IV star was this part of the picture, which has lots of nice subgroups. We didn't really, we've defined it because it's a submoid of this, but we know like almost nothing about it other than the definition. So I would hope it's finitely generated, but we don't even know that, so someone should check that. Next question is, what are the automorphism groups of the other finitely presented Johnson-Tarski algebras? Because these are just the group H classes of IV stars described before, and they're sort of independently interesting as just groups. I mean, we can solve the word problem, if nothing else, because it's a submonoid of PV. Okay, can PV be represented with a Kenner space? So you'll notice that throughout this talk, I didn't mention the Kenner set, which is really weird for a talk about Thompson's groups. I don't have time to go into it now, but like I tried to make it act on the Kenner set, and I failed for like a good reason, at least in my opinion. So I have like sort of an argument which says there shouldn't actually be a good action on the counter set in some sense. So, but maybe I'm wrong. But like I have a theorem which says if it does do stuff on the counter set, then it doesn't work this way, and I feel like that's the way it's supposed to work. So in some sense, it doesn't have a good action on the counter set, but maybe there's another reasonable action or something. I don't know. Okay. Which automorphisms of V extend to PV? So Aut V is a very important, or sort of is a highly studied group. It's described using these machines, these bisynchronizing automaton. So each, and it's sort of defined using the action of the counter set, which makes it sort of natural to try and extend automorphisms of V to automorphisms of like TV and PV, for example. So not TV and TPV, and that's all well and good, but because PV doesn't act on the counter set, it's not obvious at all how we would extend those. So we get this sort of weird thing between V and the automorphism group of V, which act on PV, and we want to know what that is, because like we don't actually know very much about the subgroups of Aut V, and more would be good to know. So next, probably the most famous of the three Thompson groups isn't V, it's actually F. And F is a subgroup of V. So is there a sort of natural version of PF, as it were, which would be contained in PV? Like probably. Partition monoids also are studied like planar ones. So like F is sort of the planar part of V in some sense. And planar partition monoids have also been studied, so that suggests these ideas are somewhat compatible. This question is other good triples. I didn't talk about good triples at all during the talk, so what am I talking about? So the reason you can define a monoid of partial isomorphisms between finitely presented Janssen-Tarski algebras is because the free Janssen-Tarski algebra is really nice. I don't have time to go into it, but this is a condition for what's called a good triple, and this sort of allows you to make the monoid work, as it were. And so you can ask, are there other nice algebras which you can make partition monoids on, not just Janssen-Tarski algebras? So just check are there other algebras which satisfy these conditions. In particular, like sets satisfy these conditions, and you can use the same construction using the variety of sets. You get the usual partition monoids. Okay. So there's a paper of many authors which introduces these things called type systems, which if you unpack are almost exactly the same thing as Janssen-Tarski unary algebras. And it turns out that congruence-free type systems correspond to a nice uncountable family of maximal subgroups of V. And because type systems are sort of natural in our context, where we bring up Janssen-Tarski unary algebras, it seems sort of plausible that this would work for the monoids. So can we get a nice family of maximal submonoids of PV, maybe, using a similar thing? And the next question I want to ask, which I think is sort of a big one, is PV co-CF? So there's famously Leonard's conjecture, which says that a group is co-CF if and only if it embeds in V, and it would be nice to have a sort of monoid analog of this. And I think PV is the best candidate because it's sort of the biggest of the Thompson monoids that have been looked at. And unlike the other ones, so IV is an inverse monoid, so it's the same as its inverse. But the thing bigger than IV, which is TPV, doesn't have that property. And if we had any universal co-CF monoid, it would have to contain its dual, because its dual would also be co-CF. And unlike TPV, PV is isomorphic to its dual. In fact, it's a regular star semigroup. So PV, I think, is a good candidate for a universal co-CF group, although I don't even know if it's co-CF at all, so that's perhaps a hard question. Okay. Thanks for listening. I definitely need to cut down this talk. Okay.